Hello, everybody, and thank you for attending this talk on scaling data ingestion for recommendation systems. I'm Aarti Basant, a software engineer at Meta Platforms, and I work with the AI Infra org, mainly focused on building reliable, scalable, and efficient infrastructure components to support ML training. AI plays a very important role for several of our products here at Meta. When it comes to ranking and recommendation models, we have products like ads ranking, newsfeed to try and predict the ads or the posts that you're most likely going to like or interact with, their stories. And we also have several content understanding models driving important products like objectionable content understanding. All this to say, AI plays a very important role at Meta platforms, and we have thousands of models continuously training inside our data centers. These models consume exabyte scale data to train, and in this talk, we want to discuss our experience on building the last mile data ingestion infrastructure to support AI training. Given the tremendous growth we've seen at Meta around AI use cases, when it comes to data ingestion, historically over the past 2 years, we've seen about 1.75x to 2x growth in the data storage size amongst data sets being consumed by training, and more than a 3x increase in just the data ingestion bandwidth between our storage subsystem and training models. Given our product roadmaps as we foresee for the future, this growth trend is going to be far more accelerated in the coming years. This makes it very important for us to continue to invest in efficiency, reliability, and scalability of data ingestion pipelines at Meta. If you look at a typical AI production pipeline, you start with training, where you train models and evaluate these models and eventually push them to products. Depending on how your customers interact with these products, you monitor and log new features, which will get stored and get utilized for the next iteration of your model upgrade. In this pipeline, we want to focus on the data ingestion components, which is the storage subsystem where you store your data for training, a system to fetch and pre-process your data before you finally push it to training. So to begin with, let's go over the disaggregated data ingestion architecture that we've built for this infrastructure here at Facebook. It mainly consists of 3 tiers: the storage tier, the data reading compute tier, and the training tier. So, as mentioned before, we have exabyte scale data that is consumed by all the thousands of training models running in our data centers. And it's very common for a single recommendation model to consume petabyte scale data. This storage capacity far exceeds the capacity we have on our training infrastructure, which means that we need a disaggregated storage tier to support training models at Meta. Typically for ranking and recommendation, models read features that we save in maps in a hybrid columnar format in a Hive table. And the storage tier is supported by Tectonic, Facebook's distributed exabyte scale file system. Next, we have the data reading compute tier, which we call DPP, data preprog tier here at AI Infra. And it mainly consists of a data plane and a control plane. The data plane is what we call the DPP worker, and it is responsible for fetching data from the tectonic clusters, decoding, decrypting the data, extracting the features that a particular model iteration requires, and then translating this to a tensor format, a format that the training can consume, and then finally doing some last mile pre-processing or transformations on the data. For a content understanding model, this last mile transformations could mean clipping an image or rotating an image. And when it comes to ranking and recommendation, these last mile transformations translate to normalization operations, bucketize operations, or combining multiple categorical features to form a new feature like using n-gram, etc. We have the DPP control plane, which is responsible for reliability features like checkpointing, for fault tolerance, and also we have an elastic controller, which can dynamically scale the resources allocated in the data reading compute tier to ensure that training never stalls for data. And then finally, we have the training tier, which usually consists of beefy accelerator-based infrastructure to support training. In the context of data ingestion, we have a DPP client in the training tier, which is responsible for fetching data from the reader compute tier and pushing it to the accelerator. Our disaggregated training data ingestion architecture has proven to be fairly flexible as we support thousands of models in our data centers, each with very different training characteristics. With the disaggregated architecture, we can independently scale different components of this system to meet each use case's infrastructure requirements. That said, our storage tier infrastructure, mainly in production, runs on HDD-based servers, while the reader compute tier mainly executes on x86 CPUs. And as mentioned before, the training infrastructure mainly executes on beefy accelerators like GPUs. With this, we want to introduce the first challenge we observe in our data ingestion architecture. Generation over generation, we are seeing an accelerated improvement in just computational throughput of GPUs or accelerators of about 2x every generation. And we cannot say that about the infrastructure components that drive data ingestion. This mismatch in growth trends between infrastructure that drives training versus infrastructure that drives data ingestion motivates us to further deep dive and improve the efficiency and scalability of our data ingestion pipelines. Any inefficiencies in our data ingestion pipelines results in stalled or wasted cycles on expensive hardware resources. This is something we really want to avoid. In this slide, we present the normalized power it takes to drive storage, data reading, and training to train certain production recommendation models. Each horizontal line represents a separate recommendation model in our production fleet, and the color coding represents the different tiers in our last mile data ingestion pipeline. As you can see in this slide, in many of our production models, the power to drive data ingestion in terms of power to drive storage or data reading far exceeds the power to drive training infrastructure itself. And now this is a problem because in our data centers, we have a fixed power budget and we want to land as many training accelerators in our data centers as possible to support the growth trends that our product orgs foresee. With data ingestion taking a high power budget envelope, this constrains the growth trend we can support within our product orgs, warranting us to invest heavily in optimizing data ingestion efficiency. So, why is data ingestion so expensive? Why is it computationally so expensive? Why does it take so much power? So, to begin with, let's understand what do data ingestion pipelines for ranking and recommendation read. And fundamentally, they read features. Now, features could be continuous values that we call dense features, properties like how much time do you spend on the platform? Or they could be sparse, categorical features like list of friends you interact with very often, or some pages you have liked, kind of indicating your hobbies. We even have another subcategory of sparse features called weighted sparse features, which associate a score to every list item. For example, at what timestamp did you like a certain page? In our production environment, we must give our model engineers maximum flexibility to experiment with features, which means they're going to want to add or remove features from their training iterations. To support this flexibility, all our features are stored in map columns so that they can easily add or remove features without really changing the schema of the data that they read. And this brings us to one of the first challenges and optimization areas we found with reading map columns for reading features that drive data ingestion. So here in this slide, we have an overview of the original layout of data for representing map features. In this diagram, in the storage subsystem, we say features A, B, C, D, and E in a certain feature column, but the user must only read features A and E for their model iteration. In the original map representation of features, features A, B, C, D, and E are represented as three streams of keys, values, and lengths. In this example, since we have fixed length features, we've represented it with three streams, But with variable length features, we may need more streams. And this brings us to the first problem, which is to read features A and E, a user must read the entire keys, values, and length streams in this example. And this leads to a bunch of inefficiencies. One, you read, decode, decrypt a lot more data than you actually need for the model by consuming the entire keys, values, and length streams. Your storage tier has read a lot more data, and you've just had a lot more network traffic between the storage tier and reader compute tier. And so we introduced this new format or data layout for map columns, which we call feature flattening. Again, in this example, your storage tier for this map column has 5 features, A, B, C, D, and E, and your user wants to read features A and E. But with the feature flattening format, instead of saving one map object represented by keys, values, and length streams, given that the map object has n potential keys in it, we represent it with n individual streams. As you can see in the diagram itself, it is now possible to selectively decode and decrypt features A and E, thus significantly improving the computational complexity of data reading in a data reading compute tier. The ability to read a subset of features in our storage tier to drive AI training within our organization, we call it feature projection. And in our production fleet, we observe that most of our ranking and recommendation models are highly selective, which means the individual models are reading a lot fewer features than actually available in the storage. And because of this highly selective nature of our workload, we've seen close to 2x improvement in many of our representative recommendation models in terms of end-to-end data reading efficiency in our reader compute tier. This graph shows the normalized gains, which has been about 2x on the data reading algorithmic efficiency. So feature flattening really helped with the computational efficiency of our data reading compute tier. But what about the storage tier? And for our high bandwidth use cases, for our high throughput training use cases, our storage tier turns out to be IO bound. But selectively reading features A and E did not seem to help as much as we expected in the IO boundedness of our storage tier. It did not seem to help the cost of our storage tier as much. And why was this happening? So when we deep dive, let's think again of the original map column where the storage tier had to fetch the entire keys, values, and length streams. These streams being larger implied larger blocks to read, which is good for the storage tier access pattern. And when you selectively read A and E, you end up incurring smaller IOs, which is not really effective with our HDD-based systems. And so another optimization we thought of was merged read, which was if the byte distance between the features you want to read is not too high, it's in the 1 megabyte ballpark, just read all the features in between. So if the byte distance between features A and E is in the 1 megabyte ballpark, read A, B, C, D, E. But this led to significant overread. That means you still read A, B, C, D in the storage tier, something that was not required. And so this motivated the project of feature reordering. With feature reordering, we started observing the access pattern of how models access features and started identifying clear subsets of features which tend to get read simultaneously. So for in this example, the user must read feature A and E, and if we identify a clear pattern that A and E tend to get read simultaneously in many of our model iterations, let's place them together. Feature reordering significantly helped the efficiency of our storage tier in the data ingestion pipelines. In many of our recommendation models, we saw 45 to 55% reduction in the volume of traffic between the storage tier and the reader tier. And we saw 30 to as high as 70% improvement in the service time of our storage tier. Now, in this talk, we've gone through feature flattening, which focuses on improving the computational efficiency of our reader compute tier, and feature reordering, which really help with the IO boundedness of our storage tier. In the blog associated with this talk, we've also discussed other important optimizations. For example, there was DPP client-side rebatching, which helped in use cases where The data reading compute tier was memory capacity bound. We've even discussed the project of flat maps, which really improved the memory bandwidth utilization for many of our use cases. All in all, through all the optimizations discussed in the blog post, we were able to improve the data ingestion efficiency by 35% to 45% in many of our production models. And so what are we working on next? In the previous few slides, we've discussed about a lot of optimizations on improving how we access data for data reading. But our data reading compute tier is also responsible for executing last mile transformations, which are model specific. And our teams are actively working on improving this component of our data ingestion pipeline with first the project of GPU preproc. And in this project, we are looking at how to move the computational components of last mile transformation from our CPU compute tier to the beefier accelerators where the hardware growth trends are more favorable. There are other industry-wide efforts in this space like NVIDIA DALI or NV Tabular, but in our production environment, I just want to outline some of the challenges we see in this space. First, most of the recommendation and ranking jobs that we see in our production environment have a reduction of data after the preproc or transformation phase. So this could be like because you're truncating or clipping features or combining multiple features to form derived features. But by pushing this transformation operation to the accelerator, we would increase the communication between the reader tier and the training tier and the data being pushed to the accelerators. And that's something to account for within our cost models. And the second challenge we are having is in our ranking and recommendation models, we tend to have like hundreds of derived features being computed in the preproc transformation phase. And each of these hundreds of derived features tend to have 3 to 5 individual operators in their computation tags. Also, given the mini batch iteration for training, this results in significant CUDA kernel launch overheads, and this is something we are trying to this is a challenge we are trying to overcome. All this to say, the idea of pushing our transformations into the beefier accelerators of training is very compelling, and we continue to work in this space. Another area where the teams are actively working is feature materialize, where we are trying to analyze and understand computationally expensive features that typically get executed in the last mile data reading step. We're trying to analyze how many of these features are really common across a large number of jobs, and then promote these features to normal features that could just be saved in our storage subsystem. In this talk, we've started with discussing how important it is for us to invest in the efficiency of data ingestion pipelines to support our product roadmaps and growth that we expect in the coming years. We've gone through an overview of our architecture and spoken about some challenges around the efficiency and just the power consumption requirements of these pipelines and some optimizations that have really worked in our production environment. And with future work, we want to mention we continue to work in this space and we continue to evolve and improve the data ingestion architecture to drive AI products at Meta. I'm happy to take any questions and thank you again for attending this talk.